Hi, my name is Skyler, and together with my teammate Nick Gong, we worked on an extra credit project for EC470 at UIUC. Our project is called Autonomous TurtleBot3 Maze Navigation. The goal was to stimulate an autonomous robot that can navigate a maze using ROS and Gazebo, applying robotics principles we've learned in class and exploring some new ones. This project was broken down into several components. First, we deployed a TurtleBot3 robot into a custom maze environment inside Gazebo. Then, we processed real-time LiDAR sensor data to detect walls and obstacles. We implemented a wall-following maze-solving algorithm based on the reactive controls instead of using a global path planning algorithm such as A*. Finally, we used the Robot Operating System, or ROS, for managing sensor data, movement control, and communication between nodes. This project has real-world relevance. The same logic behind wall detection and obstacle avoidance is foundational in autonomous driving and warehouse delivery robots. It helps reinforce skills like sensor integration, motion planning, and state-based decision-making. These concepts, such as perception, localization, planning, and control, are core topics in mobile robotics, and we were able to apply them in a realistic setting. The robot relies on its LiDAR to detect how far away nearby walls and obstacles are. Based on that, it uses the left-hand rule to follow walls and make progress through the maze. Every few milliseconds, it checks whether it needs to adjust its direction, either to avoid a wall or turn into a junction. It achieves this by publishing velocity commands, specifically adjusting angular and linear velocity through the command velocity topics in ROS. Here's how the system was architected. We built several ROS nodes, one to subscribe to the LiDAR data, one to control movement, and another for the logic that decides what to do based on the sensor input. In Gazebo, we used a predefined TurtleBot3 robot model and custom maze world. These were connected through launch files and parameter files. All communication occurred over standard ROS topics, maintaining modularity and flexibility. The math driving our decisions was rooted in two main areas: distance calculations and proportional control. We used filtered LiDAR range data to determine if we were too close or too far from a wall. Then, we used a simple proportional controller to correct our angle. Specifically, we adjusted the angular velocity with the formula v equals kp multiplied by desired distance minus actual distance. We also implemented decision logic using the left-hand rule, a basic graph theory concept used in maze solving, where the robot always turns left if it can. Here's how our wall-following algorithm worked. The robot tries to maintain a constant distance, about 0.15 meters from the left wall. If the wall disappears, it rotates left to find it again. If there's a wall directly in front, it turns right. And throughout this process, it constantly updates its motion based on real-time sensor input. This strategy, while pretty simple, is surprisingly effective in mazes without loops or disconnected components. We ran everything inside Gazebo using the TurtleBot3 Gazebo model. We used ROS2 Humble as our software platform. The maze environment was custom-made to test a variety of turn conditions and wall layouts. Everything from launching Gazebo to spinning up the control nodes was handled through a single launch file, which made testing much easier and reproducible. The final robot behavior was successful. We achieved 100% maze traversal without getting stuck. The robot consistently maintained a wall distance of about 0.15 meters and showed smooth cornering with an average angular velocity of around 0.3 radians per second. Visually, the robot's navigation was stable and consistent across multiple runs. This project allowed us to apply several core concepts from class, such as ROS architecture, sensor-based control, and state machine logic. We already knew how to subscribe to sensor topics and publish commands, but this project took it a step further. New challenges including using reactive navigation instead of using predefined paths, analyzing LiDAR sensor data, and integrating all components into a fully functioning simulation. These aspects weren't completely covered in full detail during class, so we had to learn and implement them independently by looking up GitHub repositories and searching up online. Of course, we faced challenges while trying to implement this design. First, tuning the LiDAR threshold values to accurately detect walls was pretty tricky. We also had to deal with motion instability, with early versions of the robot oscillating heavily near the corners. PID tuning helped to smooth that out, and while launch bugs and parameter miscommunications also cost us time, we realized that overcoming these issues gave us a better understanding of the full-stack robotics integration. In summary, this project helped bridge the gap between what we learned in EC470 and how those ideas are implemented in real systems. It pushed us to think beyond pre-programmed paths and into real-time decision-making using sensor data. This experience was challenging, but incredibly rewarding.